Hi, this is Mr. Kutchell, and today we're going to talk about terminal velocity. And in order to understand terminal velocity, we need to go back and review gravity and look at Newton's second law. Now, gravity is a force that likes to pull everything down to the earth at a rate of roughly 10 meters per second every second, which means that if you were falling out of an airplane, your speed would increase by 10 meters per second for every second you are falling. Now, in ancient days, Aristotle believed that heavier objects fell at a different rate than lighter objects. In 1591, Galileo set out to prove that Aristotle was wrong. To do this, he climbed up the Leaning Tower of Pisa and took up a heavy iron ball and a light iron ball. And he dropped these from the top of the Leaning Tower of Pisa at exactly the same time. And when they hit the ground, they hit at exactly the same time. And so it was Galileo's belief and others from that point on that objects of different masses fell at the same rate. So there's a picture of the old idea on the left, where a heavier object fell at a faster rate than a lighter object, but Galileo proved in 1591 that a heavier and a lighter object fell at the same rate. Now in the early 1970s, this same phenomenon was also seen by astronauts on the moon. Astronauts took both a hammer and a feather, brought them to the moon, and dropped them at exactly the same time. And when they dropped them, they hit the surface of the moon at exactly the same time. So the results seem to be very similar to Galileo's, but the key piece here was there is no atmosphere. So if we take a look at this concept only works for short distances, like the distance of the height of the Leaning Tower of Pisa, or in the absence of an atmosphere, like on the moon. Now in reality, objects don't keep accelerating forever and ever and ever. Eventually they reach a point where they stop speeding up. This is called terminal velocity. And terminal velocity, by its definition, is the highest velocity an object can reach during free fall. And this velocity can change depending upon the mass, the shape of the object, and even how high above the earth something falls from. And we'll talk about that in just a minute. To better understand terminal velocity, we're going to take a look at Newton's second law again. Now when we take a look at Newton's second law basically says the acceleration of an object is equal to the net force acting on the object, and that's the key piece, the net force divided by the mass. When we're doing this calculation, we need to remember that the acceleration is in meters per second squared, the net force would be in newtons, and the mass would be in kilograms. So now we have to look at the net force acting on an object when it's falling. Now, when an object moves through the air, that object is literally slamming into particles of air. This is something you can feel if you stick your hand out of a moving car. Air molecules slam into your hand as it is moving, creating a force called drag or air resistance. The faster you go, the more molecules your hand plows through, and the greater the drag force or air resistance becomes. Now, every falling object has a speed at which the force of the drag or the force of air resistance equals the force of gravity on that object. And at that moment it reaches that speed, the object will stop accelerating and maintain a constant or terminal velocity, because now there's a balanced force. Prior to the air resistance and gravity being equal, we had an unbalanced force and the object was accelerating. Let's go ahead and take a look at an example of this. Now here's a picture in the upper left-hand corner of somebody going to be jumping out of a helicopter and opening up a parachute. If we just isolate the person jumping out, they have no velocity to begin with, so they're not plowing through any air molecules. All of their weight is acting downward, and so the force of gravity is going to be their mass multiplied by 10 meters per second squared. So we get 1,000 newtons is what we're saying this person weighs. There's no upward force counteracting it. It's an unbalanced force, so the object's going to accelerate. Look on the right-hand side. The acceleration is going to be the net force divided by the mass. That's 1,000 newtons divided by 100 kilograms, which means the acceleration is 10 meters per second squared downward. Now if we continue to look at this, as he starts to move, notice the air resistance starts to build up. He's starting to plow through more and more air. So the net force is no longer 1,000, it's 1,000 minus 200. If we look on the right-hand side, the acceleration is 800 newtons divided by 100 kilograms. So now the acceleration is only 8 meters per second squared downward. It started at 10, now it's 8. Let's continue looking at this. Now he's fallen a little bit farther. Look at the net force. The net force is 400 newtons. Why? Because he's plowing through more air here, and he still has the same weight. So the drag, or the air resistance, is 600 newtons upward. The downward force is 1,000 newtons down, and so the net force is 400 newtons. Take 400 newtons, divide by 100 kilograms, you get an acceleration of positive 4 meters per second squared downward. Now, we reach a point in this fall where the upward drag or force of air resistance is 1,000 newtons. The downward weight is 1,000 newtons. The force is no longer unbalanced. The net force is 0. Look in this upper right hand corner. It's 1,000 minus 1,000, which is equal to 0 newtons. 0 divided by anything is 0. So this means they stop accelerating. It doesn't mean they stop moving. That would just be strange. It just means they stop accelerating. They're just going to fall at a constant velocity. This is the terminal velocity. Whatever the speed is, this is the terminal velocity. Now, typically, as you continue to fall through the air, you usually stop accelerating at about 54 meters per second, which is approximately 121 miles per hour. So that's the terminal velocity in this case. Now, what he's going to do now is he's going to fall for a little while and then open his parachute, and let's see what happens then. Okay, he fell for a little while, and now he started to open up his parachute. The parachute's not fully deployed yet, but because it's out, there's more drag, there's more air resistance. So there's 1,200 newtons up and 1,000 newtons down. Now this object is no longer having an unbalanced force. The net force, as we can see in the upper right-hand corner here, is 200 newtons divided by 100, and it's 2 meters per second squared upward. In other words, he's starting to slow down. Continuing to take a look at this, now the parachute is fully deployed. It's got 2,000 newtons of upward force, 1,000 newtons of downward force. The acceleration is now 10 meters per second squared upward. In other words, he's slowing down by 10 meters per second every second. It's still an unbalanced force. Now, as he starts to slow down, he'll start to plow through less and less air. As that occurs, the air resistance or drag will start to be reduced. Let's watch. See, it's going down, and eventually he slows down enough so that now his downward force and his upward force are the same. So now the acceleration once again is 0. In other words, he's not slowing down any longer. He's just reached a new terminal velocity, probably somewhere around 15 miles per hour at this point. So when you open up your parachute, landing at 15 miles per hour is much nicer than landing at 121 miles per hour. So this concept is so important, I want to review it again. So real quickly, when a skydiver first jumps out of the airplane, they have a force that's acting downward, which is their weight. Again, we'll say the weight is 1,000 newtons, but in this case, there's no upward force acting yet. They're not rushing or plowing through the wind yet. So as we take a look now, a little further down, what will happen is as they start to move, they'll still have that 1,000 newtons worth of downward force, but as they start to move, the air molecules will start hitting them, and maybe they'll have 200 newtons worth of upward force. The net force, in this case, the net force is going to equal 800 newtons. And that 800 newtons is acting downward, so they're still going to continue to accelerate downward. Eventually, they're going to reach a point where the downward force is going to be 1,000 newtons, and the upward force is going to be 1,000 newtons. And so at that point, they no longer accelerate. The net force here would be equal to 0. So if you have a net force equal to 0, they're just going to keep traveling at a constant speed. Remember, that's about 121 miles per hour. Actually, skydivers, if they go head down or feet down, they could get up to 200 miles per hour depending upon the situation, but usually it's 120 miles per hour. If we look at our next scene, what we'll see is the parachute is starting to deploy. At that point, there might be 1,000 newtons worth of downward force and possibly 2,000 newtons of upward force. So the parachute is going to start to slow down. The net force now is going to be 1,000, but that 1,000 newtons is acting upward. Okay, so the skydiver is slowing down. And then finally, they're going to reach a point where with the upward force, because now they're going to be slowing down so they're not plowing through as much air, when their upward force is 1,000 newtons and their downward force is 1,000 newtons, the net force is equal to 0. So the net force equals 0. They have reached a new terminal velocity, about 20 miles per hour. So make sure you understand that concept. Okay. If we look at a graph of all this, this is basically what the graph would look like. At first, as the parachutist jumps out of the airplane, they have a large acceleration, but it starts to get smaller and smaller and smaller. They're not accelerating as fast because they're plowing through the air, and eventually they reach a terminal velocity here. Then when they open up the parachute, the speed, right here, the speed goes down very rapidly, and they reach a new terminal velocity. Terminal velocity is going to be a flat line on a speed versus time graph. And then they have just reached two terminal velocities, once before the parachute was opened, once after the parachute was opened. And then they will slow down real quickly once they hit the ground. Now you might have heard in the news last October they had the highest skydive ever, and that was from 128,000 feet. Felix Baumgartner basically did skydiving from space. And he reached a speed much higher than what we've been talking about. That's because when he jumped from that altitude, the atmosphere was 1.5% of the density of our atmosphere. So basically he had very few air molecules to plow through. When he jumped out, he basically was in a spacesuit, and he jumped out and he had no air resistance. If you want to find out more about this, which I think you should, look at the website redbullstratus.com. Well, I hopefully you understand a little bit more about terminal velocity. If you go to this website, you'll find out why Felix Baumgartner was able to reach speeds in excess of 700 miles per hour in a spacesuit. Quite amazing. But I hope that you understand this concept of terminal velocity. Have a good day. Bye-bye.